Gibbs looked at the delta S universe equation and thought, well, that's nice, but as a chemist, we use delta H all the time. So instead of using delta S of the surroundings, he put in negative delta H system over T. And the advantage there is that delta H of the system, that's the delta H of products minus delta H of reactants. And chemists have always been really good about that. But obviously, this equation right now is kind of ugly. All right, negative delta H over T plus delta S, pretty funky. So he multiplied everything through by negative T. And when he did that, he got negative T times delta S of the universe equals delta H of the system by itself minus T delta S. And that looked a little bit better. But what people realized is that negative T times delta S of the universe, you can actually think about it as its own thermodynamic quality. And so what people did eventually is negative T delta S of the universe equals another thermodynamic quality called delta G of the system. And delta G is what they refer to as Gibbs free energy. And Gibbs free energy is yet another thermodynamic quality. So there's delta H enthalpy, there's delta S entropy, now there's delta G Gibbs free energy. So if you have standard conditions, delta G equals delta H minus T delta S. This is the Gibbs free energy equation. There's a picture of good old Gibbs up there. Now, at this point, you're probably like, yeah, that's a lot easier. What are you talking about? Well, okay, here's the chemist's perspective. It's easy to calculate the delta H of a reaction, delta H products minus delta H reactants. It's also easy to find the delta S of a reaction. We saw that already, delta S products minus delta S reactants. You've got a table, you'll have delta H and delta S values. Well, if you know the temperature, then you can quickly calculate the delta G value. And delta G is related to negative T delta S. So if delta S of the universe is positive because of the negative T, that means delta G is going to be negative. And if delta S of the universe is negative, negative T times negative means delta G is going to be positive. So you can relate delta G back to the spontaneity. And in chemistry, that's what people do. They're always talking about delta G values and how it relates to spontaneity. But in your own mind, just realize that delta G really comes from negative T times delta S of the universe. And this is all related to second law and stuff like that. Oh, joy. Delta G equals delta H minus T delta S is arguably the most important equation of all of chemistry because we're going to use this delta G to see if a reaction occurs or not, if it's spontaneous or not, all right? And the Gibbs free energy is just literally the energy change for the system minus the energy lost in disordering the system. So delta H now, that is the energy change for the system, and the delta S is the energy lost in disordering the system. Remember, delta S is just a measure of messiness. If you have an exothermic reaction with a negative delta H, and you have an increase in the entropy, which is a positive delta S, look what happens. You have a negative delta H minus a positive delta S. Delta H is negative, delta T minus T delta S is negative. You're always going to have a negative delta G. So if you want a reaction to be spontaneous all the time and product favored, you want a negative delta G. And you will always get a negative delta G, a spontaneous reaction, if you have an exothermic reaction and an increase in the entropy, a negative delta H and a positive delta S. Those conditions with negative exothermic enthalpies and positive increases of entropy will always be spontaneous, always product favored. But we don't always have that because sometimes you'll have, for example, an endothermic enthalpy, which would be a positive delta H, and you'll also have a decrease in the entropy, and that can be a negative delta S. We've seen a couple of those. Well, if delta H is positive, delta S is negative, but negative times negative makes it positive. In those cases, delta G will always be a positive number. So if you end up with a reaction that's endothermic and a decreasing entropy, you will always be in a non-spontaneous state. Those reactions just won't occur. They're going to be reactant favored, or they won't occur to a very appreciable extent like we've seen with equilibrium and stuff like that. So if you want your reaction to go, you want it to be exothermic with a positive delta S. On the other hand, if you do want a reaction not to occur, and there are cases of that, you want a positive delta H and a negative delta S, because those conditions will always give you a positive delta G. So delta G, when it's negative, spontaneity will happen, product favored. But if delta G is positive, you'll have a non-spontaneous reactant favored condition, and those won't be likely to occur. Let's calculate the Gibbs free energy change for this reaction, and there's delta H and there's delta S. So to do this, delta G, which is what we're after, equals delta H minus T delta S. Couple of things. Make sure your temperatures are in Kelvin, all right? Very important in thermodynamics. And second of all, notice that the units there, delta H is often kilojoules and delta S is often joules. So make sure you convert one to the other. Because our answers here are all in kilojoules, I would recommend turning your delta S into kilojoules first before multiplying by the Kelvin temperature. But anyway, plug and chug, delta G equals delta H, and you can see I just used the value as is, minus T, so 25 Celsius is 298 Kelvin, and then the delta S value, which is negative, I turned it into kilojoules. So I divided by 1,000. It became minus 0.10836. Anyway, the number came out to be a negative 568.9. Negative delta G's are spontaneous. So this reaction is going to occur at room temperature, which is pretty cool. The negative sign of delta G tells you the reaction's good to go. If this would have been a positive delta G, we would have said it was non-spontaneous. Non-spontaneous reactions don't occur by themselves. There are 4 conditions of delta H and delta S that are possible, and scientists like to think about this because it affects the sign of delta G. So we talked about earlier how if you have an exothermic reaction and an increase in the entropy, the delta G is always negative. Those are always going to be product favored, spontaneous. Those are going to be good to go. On the other hand, if you have an endothermic delta H and a decrease in the entropy, a negative delta S, then your delta G in those cases will always be positive. And positive delta Gs are the reactant favored non-spontaneous reactions, and those are hard to do. There's 2 more possibilities though. The first possibility down here is when you have an exothermic reaction but a decrease in the entropy. Now in this set, the delta H exothermic, it wants the reaction to go. A negative delta H contributes to a negative delta G. On the other hand, delta S is negative. Delta S says, I don't want this reaction to go. I'm not happy with it. So here, enthalpy and entropy are fighting, all right? Enthalpy wants the reaction to go. Entropy doesn't want the reaction to go. In these cases, then, it really depends on your temperature. Temperature times delta S can overpower delta H. If your temperatures are high enough, then temperature times that negative delta S makes for a positive number. Positive numbers don't contribute to negative delta Gs. So in this case, you would say that high temperatures make the reaction non-spontaneous and low temperatures make this reaction spontaneous. On the other hand, the last set there, it's the opposite. Now we have an endothermic delta H. Endothermic reactions don't really wish the reaction to be spontaneous, but you do have an increase in the entropy. So entropy wants the reaction to go. If entropy times temperature is able to overpower enthalpy, then the reaction will occur. So we say sometimes that in the last case there, that high temperatures make the reaction spontaneous. On the other hand, the condition right above it, we would say that lower temperatures make the reaction spontaneous, because in lower temperatures, enthalpy is able to overcome the entropy values. So these are the ways that chemists think about if a reaction is going to occur or not. And it all comes down, in this context, to delta H and delta S. But if the two of them are fighting, then you have to think about the temperature in order to see if the reaction is spontaneous or not. And remember, spontaneous means negative delta G. Those are the reactions which will occur. Non-spontaneous means positive delta G. Those are the reactions which are not likely to occur. A given reaction has a negative enthalpy and a negative entropy. What can be said about this reaction? Okay, so if it has a negative enthalpy, that's exothermic. And a negative enthalpy does contribute to making delta G negative. But if the entropy is negative, negative times that negative right there makes for a positive term. So entropy here does not want this reaction to go. So this reaction is not product favored at all temperatures because enthalpy and entropy have the same sign. If they have the same sign, then that means they're fighting, all right? And these have the same sign. They're not, one of them is not happy with this reaction. So it's not product favored at all temperatures. It's not product favored at any temperatures either. If you have them being opposite signs, that would be the case of A or D. So if they're both fighting, all right, you have to think about which one wants the reaction to be spontaneous, i.e., which one wants delta G to be negative. And delta H here wants the reaction to be negative. It's a negative delta H. So what we would say here is that if the temperature is lower, all right, then the lower temperature times delta S, which gives you, by the way, a positive number, it won't be larger than the negative delta H. Low and high here are very relative. It depends on the magnitudes of delta H and delta S. But at lower temperatures, delta H should be able to overpower delta S, making the reaction product favored and spontaneous. On the other hand, at higher temperatures, then negative T times negative delta S makes for a positive value. Positive values can overpower delta H if they get large enough, and you'd have a non-product favored reaction.